from where we stopped last week. Okay, last week we were talking about tension in the string or a rope. This tension, it cannot, the rope, they cannot, how to say, it cannot be straightened by itself. We must apply a force, okay? A force by pulling it or hanging it onto a weight. So the string or the rope will straighten. In this way, the force or the weight of the object is transmitted along the rope or the string to the other end. We have two situations here. One where the object is in equilibrium. That means the object is not moving. All the forces, they balance one another. So it means the upward force is equals to the downward force. The force to the left is equals to the force to the right. So we have equilibrium. And at the same time, we also have cases like the object is accelerating. Like for example, in case number 2, the object is moving, not with a constant velocity. Even if it's moving with a constant velocity, there's still no net force. But it is moving with acceleration or deceleration. So in this case, there is no equilibrium. When the object is not moving, we say that the object is in equilibrium. Equilibrium means all the forces, they balance one another. The net force is 0. Okay, so that is case number 1, and moving, accelerating object is case number 2. Right. So we look at case number 3. In case number 3, it is something like this. An object, it is hanged by 2 strings. These 2 strings or 2 ropes, they are at the same angle with the horizontal. So that means we have one string on the left hand side, another string on the right hand side. These 2 strings, they are at the same angle with the horizontal. They produce a symmetry. Okay, so by symmetry, the angle are the same. The force also, they are the same. The 2 forces, they are the same. Okay. Altogether, when we look at this object hanging by 2 strings or 2 rope, there are 3 forces acting on this object. Okay, one is the weight, and the others, they are tension number 1 and tension number 2. But because the 2 tensions they are the same, so we call them only tension, right? So the tension, the force produced by one rope is the same as the force in the other rope because of symmetry, right? So the force diagram is like this. The force diagram is like this. Okay, so we have a point here, the center of gravity of the object. It is pulled upwards by 2 strings. Okay, the first string produces a tension of T, and the second string also produces a tension of T, but and in different direction. The angle, the size of the angle is the same, but they are pulling the object upwards in 2 different directions. And these 2 tensions, they are balanced by the weight of the object. Okay. Okay. Right. So if this is the case, if the 3 forces are at equilibrium, okay. So we are going to resolve the 2 tensions into their vertical and horizontal component. Okay, so the 2 tensions, they are shown by the 2 red arrows here, 1 towards the right hand side and the other one towards the left, but a bit upwards. So we are going to replace the red arrow with the blue arrows. In this case, the angle is the angle with the vertical. It's not the angle with the horizontal. Let me draw this angle. Let me draw this angle. Okay, this one. Okay. Now this is the angle with the vertical. This is the vertical line, and the angle theta is the angle with the vertical. On the other side, the tension makes an angle of theta degrees with the vertical. So we have two tensions. They are making an angle of theta degrees with the vertical. Now, when we replace the red force with the two blue forces, we are actually resolving the red arrow, the tension, into its two components. The vertical component is adjacent to the angle here. So adjacent is cos. So this blue arrow, the vertical blue arrow, the magnitude or the size of the tension is t cos theta. Okay, t cos theta. The horizontal component, which is not adjacent to the angle theta, you see, there's no theta here, so it is not adjacent. So not adjacent, this component is t sine theta. Okay, t sine theta. So actually, when you resolve the red arrow into the two blue components, this red arrow no longer exists. So it is replaced by the two blue arrows, Now, similarly, on the right hand side, the tension in the string T here is replaced by its two components. The vertical component, which is adjacent to the angle, is t cos theta. So we have to remember that adjacent is always cos. The component that is horizontal here, the horizontal component of the force, is t sine theta. So once you resolve the red arrow into its two blue components, the red arrow no longer exists. You just replace the red arrow by the two blue ones. So closing the two red arrows, I can see there are four forces there. Two vertical component and two horizontal component. Now these two vertical component and horizontal component, they are balanced by the weight. If you look at the diagram here, so they are balanced by the weight. The weight is actually acting downwards here. The weight is acting downwards and it is mg. Okay. So when you compare the forces, comparing the vertical component of the forces, the vertical component, they are t cos theta, t cos theta. Now these two forces, they are balanced by the weight mg. So to form an equation, it becomes like that. T cos theta plus another t cos theta, and this is balanced by the weight mg. So the two terms, they are the same. You can add them up and it becomes 2t cos theta. Okay. If you want to find the tension in the rope, you just move the others to the right hand side. So the 2 and the cos theta, you move to the right hand side, it goes to the bottom. So the tension in the string is actually mg divided by 2 cos theta. So this is how we find the tension in the string. Okay, the size of the tension is mg divided by 2 cos theta. This is the magnitude of the tension, right? And If you compare the horizontal component, you can see that this is t sine theta, this is t sine theta. So the two of them have the same magnitude but in the opposite direction. So they balance one another. This is also why we say that the two tensions, when the angle they are the same, the two tensions they are the same, right? Because you cannot have here T 5 newtons, this T is 4 newtons when the angle is the same. If the angle is the same, this is sine theta and the other one also sine theta. So since these two components they are the same, the angle is already the same. So we can compare the tension. So the two tensions they must be the same. If they are not the same, then the two tensions they cannot balance one another. Okay, so bear in mind that if the angle is the same, the two tensions must be the same. This is different from the case of non-equal angle.